Alright, you guys. So for this lecture, let's talk about sensation and perception, and how those two different phenomenons work. So the key question, how do we do it? So the difference between sensation and perception, sensation is the activation, the physical activation of any of our sensory organs, our retina and our eyes, um, uh, the hair cells in our ears for hearing. Sensation is just uh, the um, starting the nervous system process. Um, because, say, for example, the retinas in our eye, those are nerve endings. Being able to take physical stimuli, like a light wave, and start to turn it into neural code. So sensation is the activation of our sensory organs, and perception then is our nervous system being able to figure out and sort out and understand the information that is coming in. Um, our vision knows that that color is pink. We know that that is yellow. We know that is white. Um, we know how something feels without even necessarily having to touch it. We hear something and we are able to recognize, for what it is. So, when it comes to the act of sensation and perception, top-down processing and bottom-up processing talk about what kind of drives things forward, um, which comes first. And in either of these cases, it talks about how one can be more of the driving seat than the other. So in top-down processing, the P stands for perception, meaning that uh, some sort of higher order cognitive capability is kind of guiding our where we should put our senses. For example, um, like say you're driving in a car and you are looking for a specific exit to take. You are using your attention and your memory to tell your eyes, so to speak, what to look for. Um, Bottom up processing, on the other hand, um, is uh, something that is more sensory driven, meaning like let's say you're just sitting still and then you hear a loud sound. That loud sound catches your attention and pulls your perception towards it instead of actively looking for it initially. So top down just says that perception is guiding our senses. Bottom up is saying that our senses are guiding our perceptions. Okay, so let's talk a little bit about sensation. This is just showing you how sensitive we as humans are to different types of stimuli. We are very good at it, picking up on things um, for each of our senses. The absolute threshold is the minimal amount of stimulation that is needed for us to be able to detect the presence of a particular stimulus. So like how much, odor is required for us to detect that it is, that we can smell something. And we need to be able to detect its presence with accuracy 50% of the time to find out what is the minimal threshold, the absolute threshold, the minimal amount. The difference threshold is how much stimulus is needed um, to notice that a change has occurred. So for example, like if we were in class, what I would do is I would have one of you hold out your hand, and um, I would place like 10 nickels or 10 coins into your hand. And then I would slowly add other nickels without you hearing it, hopefully without feeling it. But I would ask you, when do you feel like the weight has changed? And that is how much difference is needed, uh, how much needs to be added or how much needs to be taken away before we can notice that a change has even occurred. So sensory adaptation, also known as habituation, is when we are in the presence of a constant stimulus, but because it is constantly there, we actually end up not noticing it as much anymore. A simple example would be whenever you are, wearing clothes, the shirt on your back. Before I said that, you probably weren't actively thinking about um, that stimulus being present. But now that you think about it, you can, you know, feel it again. The reason why we have this is because it's useful because we only have so many cognitive resources available to us to pay attention to things. Um, we don't want to be constantly thinking about the sensation of the shirt on our back. That would slow us down, keep us from being able to focus on other things. Um, but the idea then is that um, um, we would be more readily available to detect new novel stimulus. If like something flies in from out of your field of vision, you want to be able to detect that so you can protect yourself. So all of our senses have different sensory thresholds, and they all have adaptation capabilities. Um, this down here is just something to mention where, for example, so vision, hearing, touch, pain, and taste. Um, some neuroscientists have argued that the sensation of pain is a sixth sense and that it is separate from, say, the ability just to touch. Um, there are some people who are born who can, feel things like tell that that is smooth or, tell that that is hard, but they don't feel pain. So some people argue that pain is something completely separate from touch. This is just showing you the light wave spectrum and the properties of light, the wavelength and amplitude change. As that changes, then the energy signature changes and light steps into our vision capabilities. So this is a breakdown of our eyeball. And one of the interesting things here is that whenever some sort of visual stimulus passes through our lens here, it actually gets flipped upside down when it hits the retina. Our retina is all of our photoreceptors chilling, hanging out on the back of our eye, but then the image is actually upside down, and then our brain fixes it again, which is actually kind of cool. This blind spot here, so our retina forms together to form the optic nerve as it exits out the eye. And these are nerve endings all along here. These are like extensions of our brain sticking out into our eye, which I thought has always been cool. But this is considered the blind spot because where the nerve exits out the eye, that little piece there can't be any photoreceptors. So I've always thought that was cool. Um, Sorry, I think I found an angle that won't have it be scattery. Um, so our iris, this is what determines the color of our eye, but these are little connective tissues that pull open our pupil to determine how much light can be let in. Um, and our lens can fatten up or flatten out. Fattens up for things that are closer to our eye, it flattens out for things that are further away. This is a breakdown of what our retina looks like. These are just the different photoreceptors. On the way back, light is coming in through here and then hits our photoreceptors that start the transduction process of us being able to see things. Something worth noting is the difference between rods and cones. Um, rods and cones are the different types of photoreceptors. Rods respond to grayscale, cones respond to light. We have a much higher amount of rods than cones. These rods are much more sensitive, meaning not as much light is needed to activate them compared to color and visual acuity of cones. This is just to show you just how big our pupils of like cats can get, but that's because they're very good at seeing at night. They have a higher density of rods to cones than even we do, so they're very good at night vision. Dark adaptation, light adaptation, the amount of time it takes for our rods or cones to turn off or turn back on, and the rapid adjustment of light turning on or turning off. I'm not going to hold you guys to this, but this is just to show you the breakdown of the sequence of events that happen uh, to go from our eye all the way up to our visual cortex. The optic nerve. Um, so uh, each hemisphere of brain tissue gets represented into each eyeball. That is evolutionarily set that way so that if we lose one eye, we still have both visual fields present for processing for our two hemispheres. Feature detectors. This is kind of cool. So this monkey here has got a recording electrode implanted into the back of his brain, into his occipital lobe, and basically what is happening for him is he's looking at this bar and it's changing its orientation angle, and this shows the activity of the specific cell in his occipital lobe in response to the visual stimulus. And as you can see, when it's at one orientation, it fires a lot. The cell fires very rapidly. You change the orientation just a little bit, and then it starts to slow down. Change the orientation more, then the cell doesn't fire anymore. So what that means is that we have specific cells in our brain responsible for allowing us to see visual things at different angles. And there are people, or not people, there have been experiments done where, say for example, cats, they are deprived of the ability to see anything, at a horizontal angle. They are blind to them essentially. So just another reflection of specific biology to specific ability. Supercell clusters. This is just speaking how groups of cells work together on the same common thing. Let's talk a little bit about hearing. So hearing, the louder it is, means the bigger the amplitude, the bigger the size. The pitch then, a high octave or a low octave is going to be in the space between the crests from one to the next. Sorry, I'm trying to make this so that you don't see all that visual noise. Okay, so with hearing, it's kind of cool how it gets broken down. So inside of our ear, we have this kind of snail-looking like organ called the cochleae, and inside of it is this thing called the basilar membrane. And the basilar membrane is kind of like a sheet, like your bed sheet. Like when you shake it, your bed sheet, it'll start to ripple, right? Well, the way that our eardrum is set up is that when sound comes into our ear canal, hits up against the eardrum, these three bones then, the malleus incus and stapes, they're kind of like the arm that is holding on to this basilar membrane. And based off of the sound wave that's coming in and hitting up against the eardrum, it's going to cause the shaking. It's going to cause this sheet to ripple and wave, pulsate, and then hair cells all along the way are just waiting for that sheet to kind of bump up against it. Skipping ahead, these are the hair cells, and the basilar membrane is this kind of waving, and if it hits up against this one, like taps it, that is what signals for hearing to occur. Like that means that this pitch or this frequency has been hit, and then we can start to hear it. Being able to locate sounds really breaks down to which eardrum on the right or the left gets activated first. So when this gets activated first, the sound signal gets sent to the center of our brain. The time difference then of our right ear versus left, when our left ear gets activated and sent here, then it's basically telling us, which ear got activated first to help us orient to tell where the sound came from. Okay, so let's talk a little bit about different perception things then. So as I mentioned before, sensation is the activation of the physical receptors, or the sensory receptors of physical events. Perception is organizing that info. So how it all gets broken down. Talked about bottom up and top down already. This is just to reiterate that. So, when you really break it down, like when it says here, it is Wednesday, we see that as 3 words. But when you really break it down, it's just a lot of individual pieces of information. How we know to automatically group it together. Context is important for it. So when you look at this here, what do you see? A, B, C, D, E, F. 10, 11, 12, 13, 14. Well, this and this are the exact same stimuli, but we know how to interpret it, how to make perception of it, based off of what it is being surrounded by. Context can be very influential. This is just a show. If we were in person, I would ask you guys to all read aloud what these different words say, and then compare it to this. And basically, when you go through it, the importance of context, you'll notice that when you try to read this paragraph out loud, you can almost read it at a normal pace, because when you see the word in a setting, the context of a paragraph, you know better what it means or what it's trying to get at. With perceptual organization, the most common school of psychology in this is Gestalt. Gestalt is a German school of psych that focuses on the whole. Gestalt's main idea is that the whole is greater than the sum of the parts. What they mean by that is, if anyone is like a basketball fan, a team of players, 5 individuals come together and become a team. The team achieves something that the individual pieces couldn't. Music is another great example, where the whole achieves something more than just what the individual parts added, on their own. What I mean by that is, like when you listen to music, you hear the different instruments, the different sounds, the vocals, if someone is singing, and it all comes together and creates like a melody. Well, the melody is that gestalt moment where everything comes together and transcends into something greater than what the individual pieces could do just completely on their own. With form perception, this is the idea of figure and ground, how we can see two different things. Like here, you will see two faces facing towards each other, and then you'll also see this chalice. When you see one thing, the other thing goes into the background. The thing that's popping out towards you, when you pay your attention to it, that's the figure. And ground is the background. So this then just breaks into different Gestalt ideas of how we will group things together, closure, proximity closure. I mean, you guys see a panda here, right? Well, when you really look at it though, like there's no outline of the panda's head. It's just white space. And then the presence of his ears is what gives us the clue that, this is his head. Proximity, grouping something together. Like when you look at this here, you almost kind of see like a tree, so to speak. But really, it's just individual pieces of information, but because they are close to each other in proximity, we group it into being one thing. This versus this is the same idea. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There should only be 9, but they're 9 individual pieces of information. Over here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of information, but we see this as one cube or one piece. So the idea of grouping principles. Same idea, similarity. Probably see this in lines of color instead of just 16 individual pieces. Things we connect, even though it's not actually physically connected, we will interpret it that it is. And then continuity with this Y line here, we still see it as a smooth, continuous thing, even though there's something cutting right down the middle. This is just something testing if we have the ability excuse me, if we have the ability for depth perception, if we're born with it. And the basic idea here is that, so this is a glass table, and the infant is put here and is coaxed to try to crawl across. Well, the idea here is that if the infant does not have any depth perception, they will not notice that there is any change. To them, this pattern would still appear as if it was up here. And we do appear to be born with an ability of depth perception because the kid won't cross over, even though they can feel the glass. They interpret it as there's a drop off here. And so they're like, are you crazy? I'm not going to risk my life. But because they are able to generate that depth perception. So we are very good creatures at, finishing patterns detecting patterns, but because we try to finish patterns right away, we may not realize that we are being tricked. So I'm going to change this for a second, just to show you guys. But basically, so because of the orientation of these arrows, which one would you guess is longer? The red or the blue line? Now, let's see. The red one goes to right from there to about there to there. Blue one, same idea. So even though it looks like it's significantly longer, it's not, just because of the orientation. So again, I ask you guys, if you compare this line here to this line here, just by looking at it, it looks like this one is bigger, longer than this one, right? But in fact, they are the exact same. Let's do it again. All that is showing is just like clicking and dragging, pulling that over. It's like right around here, it seems like it becomes bigger. But they are the exact same. When you look at this, would you say that both of these gray dots are the same brightness, but then based off of context? Did you see that? There was a moment where this one almost looks like it changes brightness because of what is being surrounded by. Size, distance, same idea as the lines before. What we think is further away. So which one do you think feels bigger? This one or this one? The thing is that, you know, as you can probably guess, they're the same size, but we feel like this one's bigger because when we look at this road, we think to ourselves, oh, as we go down the road, it's getting further away. So this one, by illusion, seems to be larger, when in fact they are the exact same size. Okay, that is sensation and perception, you guys. You'll see an assignment for you to work on for this. Let me know if you have any questions, and have a great rest of your day.